Thank you. Okay. Technical problems always. Okay, thank you for inviting me to have a presentation here today. I don't know the background for having this presentation, but you probably know this is for an EU project that both VTT and this university are working with, but I'm not personally working in that project. But I was asked to have this presentation because I was visiting here anyway today. Okay. So I'm going to talk today about mainly about inkjet printing and why it's a suitable method for printing functional inks. But I'm also going to explain how to formulate inks for inkjet printing and how to optimize the printing process in order to achieve suitable structures. And then I will show some examples that we have developed at VTT. And thank you for my colleagues who have helped me preparing this presentation. But first, a few words about myself. So I'm Liisa Hakola, and I come from Finland, and I work there at VTT. That is a Technical Research Center of Finland, and I have been working there since 2002 after my graduation from Aalto University School of Science and Technology. And my background is in graphic arts. So what that means is printing technologies, but also media technologies. And I did my master's thesis about how the inkjet ink composition affects the print quality. So my background is in printing and in the process. So I might not know all the details about the electronic devices to print well, to summarize things. And I have worked in many areas at VTT. My position at the moment is a senior scientist in a research team called Printed Sensors and Electronic Devices. And okay, I have had several presentations and I have some peer-reviewed papers. And I'm also a certified project manager, and my time is focused on project management, so not too much research nowadays. A few words about VTT. So we are the Technical Research Center of Finland. There is almost somewhat more than 2,000 people working at VTT nowadays, and biggest research organization in the Nordic countries in Europe. And there are so many people. We are organized in 3 business areas. It's knowledge-intensive products and services, but we also have areas for smart industry and energy systems. Well, you can read yourself. It's about transportation and nuclear safety and industrial processes. And then we have solutions for natural resources and environment. So that's about biotechnology, process chemistry, and so on. Knowledge-intensive products and services. So, well, how should I summarize this? This is kind of, we are focused around certain solutions like health, connected society, and industrial internet, but we also have special manufacturing development like this printing-based manufacturing processes. But we are using this printing technology in all of these areas to develop certain solutions. I'm talking about printed functionality, so I should first explain what it means. So this means the type of components and systems which extend the functions of printed matter. So to simplify, it means electronics electronics that is made by printing, but it can be also other things like printed sensors, it can be printed optics, printed power sources. And all of these devices that are created by using printing methods, they might not have the similar performance when comparing to silicon-based electronics. But the idea is more like to create new types of application areas and embed functionality into the type of products that currently don't have functional features. So it's kind of enabling technology to create intelligence everywhere. Also in my presentation I will talk about sensors, but then I will talk also about indicators. And so the difference between these two is that sensor is a device and it creates an output that is a signal, and that signal has to be converted into a human readable form. But an indicator is it's kind of a sensor based on optical reading, so it doesn't require special signal converting or a reading device. It's just, for example, detecting a visual color change. So here are some of the enabling technologies that have made it possible to make printed functional solutions. Of course, there are high-speed printing methods, and those have been here for several hundreds of years, at least some of those. But one important thing is that there has been a lot of material development for achieving this type of solutions, such as metal nanoparticles. That is one thing. The particles have to be nano size in order for them to be printable and produce the kind of performance that is required. Another material are conductive polymers. Those are also easily printable. And also there are many biomaterials that can actually be formulated into printable inks. And of course, there are these materials, but then they have to be formulated into inks. And in this formulation process, certain things have to be considered, like the particles can't agglomerate because that will interfere with the printing process. And also when formulating the ink, the particles or the functional matters, they can't lose their ability to perform in a device. So those have to be considered during ink formulation. And also these online drying and sintering are important. For example, when printing nanoparticle inks, they have to be sintered by using, for example, very high temperature curing. But sometimes the nanoparticles might require one hour to actually sinter. So there is no point in printing the actual structure in just a couple of seconds when you have to cure it for 1 hour. So it's good that these type of technologies such as photonic sintering, IR sintering, and so on have been developed to speed up the actual production process. Here are some examples of what type of devices have been made by using printing processes in general. So there are OP foils, solar cells, energy sources. OLED displays are a very large area where the development has been made. Microfluidics, optofluidic sensors, and also other printed sensors that can be created. And here are some printed memories also. And all of these devices have been mainly created on substrates that are flexible or even paper. So this is one benefit of using printing technology, because then flexible substrates can be used, and this opens a possibility to create new types of solutions. But now the actual printing methods. So the printing methods are traditionally divided into analog printing and digital printing. And analog printing means that there's a physical master that creates the image on the substrate. So this physical master is a printing plate. And for example, in gravure printing, there is an ink fountain, and a gravure cylinder sort of picks up the ink from the ink fountain when it rolls. And this physical master, this printing plate, is attached around the gravure cylinder. And the amount of ink is leveled by using a doctor plate. And then this gravure cylinder is squeezed together with an impression roll, and the substrate goes between those. This is called a printing nib, and then the ink is transferred to the substrate in this nib. Flexography is kind of similar technology, but instead of using this doctor plate, the leveling of ink is done by using an Anilax roller that moves the ink from the ink fountain or whatever it is to the printing cylinder, and then there is the printing substrate. And the screen printing is a bit different technology. There is a screen that has holes, and these holes form the image, and the ink is squeezed through the screen, and then the image is formed. But in all of these, there is the printing plate that has the actual image that is to be printed, and then the ink is put onto this printing plate and transferred to the substrate. But in digital printing, there is no physical master. The image is created from a digital file, like when you use an office printer, you just click print and then you get the picture. There is no printing plate making in between. And the most popular digital printing method for making functional things is inkjet printing. And this is based on a print head. It's like when you use an office printer and you put the thing, where is the ink? That's actually the print head. And inside the print head, there are channels where the ink travels, and then the ink drops come out of a very small orifice or a kind of hole that is called nozzle, and then these ink drops go into the substrate and form the image based on the digital file information they get. And there are different inkjet technologies. There is continuous inkjet that is used for this type of coding and marking applications. There is a constant generation of ink drops, and those ink drops that are required for forming the image are guided to the substrate, and the other drops are recirculated. But as you can imagine, for printing some functional material, this is not very good if you all the time recirculate the functional stuff and reprint it all the time. So this continuous inkjet is not used for functional solutions. But then there is drop-on-demand technology, where the drops are generated only when they are required. So there is no ink recirculation. And this is, of course, a better technology for printing conductive materials, for example. And there are also subcategories, like in thermal printing. The drop formation is based on a very high temperature during drop formation, and again, that high temperature might not be preferred with functional inks. But in piezoelectric inkjet, the drop formation is based on a deformation of a piezo ceramic element that creates sort of an acoustic pressure, and that's not too dangerous for functional inks. So in most cases, when people say that they are using inkjet printing for printed electronics, for example, they are using this piezoelectric inkjet. So there are these printing technologies, and then when starting to develop something, a suitable printing method has to be chosen, and this has to be done based on the targeted device performance and also the production requirements. For example, with the analog printing methods, it's easy to get high throughput, very high viscosity inks can be used, and very thick layers can be produced. So in many cases, analog printing methods are good methods. But if very small batches are required, like the layout changes many times, or very thin layers are required, or very expensive materials are printed, then inkjet printing might be a better choice. And also this, the target feature size has an effect on the choice of the printing methods. Inkjet printing typically produces details that are even in the range of 10 to 50 micrometers, and screen printing produces somewhat bigger details. So also this has to be considered, what are the targeted feature size. Of course, inkjet printing is not, at least not currently, possible to compete with lithography when considering the feature size, but printing methods are not trying to replace lithography, so this is not too essential. Okay, so as I listed, these are the benefits of inkjet printing when making functional structures. So the material consumption is quite low. Not much of the ink is consumed during setup, so the ink is not wasted too much. And when printing expensive materials, that is very important. Actually, when doing ink formulation, this is an important thing to consider because the functionality of the ink has to be maintained during the whole printing process. And this is why there are these typical challenges also when considering inkjet printing for printing functional stuff, because sometimes the inks are not very stable because they have to go through very narrow channels, and so that might interfere with the drop formation, and then these type of phenomena like missing nozzles can exist. Like here is, if you can see, here is one of the printhead nozzles hasn't been working correctly, so there is a white area, although it should be also printed with silver. Something weird going on also. So all of these issues has to be considered, and already during ink formulation, but also during process optimization in order to avoid these type of issues. And this is also a very typical issue for inkjet printing, that there are these so-called satellite drops outside the actual area that was supposed to be printed. And these might be avoided by optimizing the printing process, but also optimizing the ink. Okay, I will explain some of these things later, but here is a variety of things that we have developed at VTT by using inkjet printing. So we kind of divide our expertise into electronics and optics. So there are antennas, conductor grids, and similar type of things. And then in the diagnostics and product safety area, we have these sensors and indicators and other similar things. And here is actually some of these inkjet printing things have already gone into the industrial scale. So there are these type of devices already available and in use, at least in development stage, for making OLED elements by using inkjet printing. So actually, when considering what technologies are the most mature one, these are these LCD and OLED display elements, and that are the most developed things at the moment. Okay, but then if we start thinking about how to develop something based on inkjet printing, so there are certain things to consider. First of all, the ink formulation, then the drop formation during printing, layer formation, how the substrate and ink interact, ink drying, and finally the upscaling from the lab to the industrial scale. And okay, I will explain this in detail. So when developing an ink, these are the important things for printability. So there are certain values that for viscosity, surface tension, and pH that have to be met in order an ink to be printable by inkjet printing. And in inkjet printing, these type of phenomena should be avoided. Foaming of the ink, that is typical for water-based ink. Sedimentation means that the ink adheres to some surfaces inside the printhead, and also the agglomeration is not desired. As you can imagine, if there is a very small nozzle that the ink has to come out during drop formation, and the diameter of this nozzle is between 20 to 50 micrometers. So there can't be very large agglomerates in the ink because they can stick into the nozzle, and then that nozzle isn't working. But also when considering the performance of the functional ink, or also the functional material loading is important. The material loading might not be very high when formulating inks, so it has to be considered what is the sufficient level for the performance, but also for the printability. But the good thing about inkjet printing is that the performance of a printed structure can be increased by using more than one printed ink layer. With inkjet printing, it's quite easy to print multiple ink layers. And then, of course, how the ink interacts with the substrate is also important. So here is how the drops come out of a nozzle. So those are the small nozzle orifices where the drops come. This is just a reflection, so don't mind about that. So there is a small, when the drop comes out, it has a very long tail, and this tail has to disappear before the ink drop actually lands onto the substrate. And sometimes from this tail, a very small part here can sort of separate, and then it flies wherever because it's much smaller, and those are the satellite drops that we don't want. And here is the operating window for inkjet fluids. So these are actually quite strict areas where that the inks have to meet. The viscosity has to be between 10 to 20 centipoise, so that's not very much. And also the surface tension is critical. If the surface tension is too high, the printhead is not kind of wetting, and then there is no drop formation. And also, as I explained, the particles have to be much smaller than the actual nozzle diameter. And also the volatility of the solvents that are used has to be considered, because there are so small drops, and if the solvents are very volatile, then that causes the solvents disappear, and only the functional stuff is left, and that can start to dry already into the printhead. So high boiling points are desired. And of course, here is whatever can be formulated for inkjet can be printed. So there are a lot of materials that can be done. Sorry. Okay, here is just an example that shows how changes in one parameter, in this case in ink viscosity, affects the drop formation. So this is like a viscosity here is too low, so there are multiple breakups, and this means these satellite drops are flying everywhere. But when the viscosity is at the proper level, then there isn't any, and then we get a good print quality. So after the ink is printed, then we have to get a good layer formation. Of course, this has a lot to do with these contact angle issues, but also because in inkjet printing we are printing drops. So if the process is not controlled good enough, we might get this result or something like this. This is a compromise between the printhead settings, the substrate properties, but also the printing resolution, for example. So it's kind of, it's actually quite tricky to get a structure like this. So the whole process has to be controlled very well. And then after the layer is printing, of course, the ink has to be dried. In an inkjet ink, there is a very high amount of solvent. And during drying, we have to get rid of that solvent. So sometimes even 95% of the ink can be a solvent. And during ink drying, that solvent has to go somewhere. So in a traditional printing, when printing a traditional ink on a paper, the ink penetrates into the substrate that kind of absorbs the solvent, or it's evaporated, or when using UV curable inks, the whole ink hardens. But since there are so much of this solvent, and also because with the nanoparticle inks, this sintering process where the particles create a continuous layer requires some method. There has to be new types of methods for curing, waiting for something to evaporate, or if using a plastic substrate, the solvent just can't absorb into the substrate that is not porous, then these type of methods are very important for curing. And here are some examples of the type of ink recipes that we have used at VTT. So this is an example of an ink that is that has water as the main solvent. So there is water and then an alcohol, and together these are already 85% of the liquid. In this case, we have a binder for getting good adhesion with a plastic substrate, and then a surface active agent is required because water has such a high surface tension that it has to be made lower by using a surfactant. And then finally, the functional substance is only 10% of the whole ink. And here is another example where the main solvent is alcohol and only 10% of the water is used. So in this case, no surface active agent is required. Okay, I briefly just show what type of machines we are using at VTT. So these are mainly for the analog printing, flexo printers, screen printer. No, that's not screen printer. Yes, that's a screen printer. Yeah. So those are the lab scale machines, but then we also have these huge printing machines that can do very fast roll-to-roll printing. And this is our golden star that has received awards, but this is a very good printing unit, and it's a pilot scale printing, so you really get an idea how things work in an industrial scale. But for inkjet printing, we have something similar, like you have in this, not in this building, I think it's another building, but this Pixtro printer. But then we also have this Dymatics printer. It's it's a cheaper device, but it's and this big stroke printer is more accurate, but they can mostly do the similar things. And then we have this XY table-based printing system with 4 printheads that we can also use. And here is how our laboratory for inkjet printing looks like. So there is a clean room facility. It's not as clean as clean room facilities for making lithography, but this is like a semi-clean facility. You have to have special clothing and so on. Okay, but at VTT, because we have those pilot scale big machines, we do a lot of experiments with upscaling. So we develop something in laboratory, but then we move into the pilot scale. And there are some considerations, especially with inkjet printing, when moving from very small scale to very large scale, because there are, for example, much higher printing speed, and also the dry voltages and firing frequencies are much higher, so the inks are exposed to much higher forces during printing. So that might create difficulties when moving from lab scale to production scale. And that's actually one reason why we have, with our big stroke printer, we can also use industrial scale printheads. So we can already, during ink development, get an idea how the things might work in the industrial scale. So it's like getting something to work in laboratory might not work in production scale at all, unless those issues have been considered already beforehand. But still, some of the compromises have to be made when in industrial production, like with the printing speed. So in industrial production, it's, of course, the intention is to have high throughput, but if you are printing in very high speed, to control the printing process and the drops might fly wherever. So sometimes it's just compromises have to be made. Okay, so now some examples. So these are the indicators I mentioned at the beginning of my presentation. So these are not sensors. These are based on color chains, like in this package of fish. So these are indicators. They are yellow when the package is okay, but when the package is leaking, or if the food is starting to spoil, then the color changes, and you can check immediately if the food is okay or not. And this can be used for many other purposes also, like we have developed indicators that are indicating these type of conditions, so even for water quality. And mainly we have used inkjet printing technology because it enables us to print directly onto, for example, package, and the printing can be done during packing. It's more easier to add a small inkjet printing unit into an existing production or packing line than adding a big flexo printer, for example. So that's why we have chosen inkjet printing in most cases. And here are just some references, oxygen indicators. So this means that when the package is leaking, a yellow area changes into a blue area. And similar to, this is a humidity sensor. If the package or a product is in a too humid condition, something happens. In this case, I think this is some Eastern European language for fresh, and then this word disappears. Okay, and then there is also one freshness indicator and time temperature indicators that we have also worked with. For the sensor area, we are also doing a lot of work with paper-based diagnostics. The goal is to develop low-cost, easy-to-use disposable test that can be used at home or at point of care, and the person using the test doesn't need professional skills from the medical area. And for this, we have developed our patented technology. So in the previous presentation, there was about using wax printing to make the similar type of channels. But we have developed method based on flexo printing that makes the areas around the liquid channels hydrophobic. So it's kind of the same as with the wax printing, but it's a different type of material that we are printing. So this actually shows the, let's see if the video is working. Okay, no, you can't see it. Why not? I can see it.